So here's a crash course in algebraic number theory. So K is an algebraic number field. Means it's a finite extension of the rationals. Okay. Inside this field, there's a collection of elements. Alpha satisfies a monic polynomial with integer coefficients. So all the collection of elements in capital K that satisfy, that are the roots of a monic polynomial equation with integer coefficients. You look at that totality, and it's a beautiful theorem of Dedekind that this set is actually a ring. So Dedekind showed OK is a ring. That's a nice theorem. And this ring is called the ring of integers of K. We call this ring the ring of integers of K. Now, Dedekind and many others at the time were motivated to study these rings, actually in their attempt to prove solve Fermat's last theorem. So as I've often said, major unsolved problems are kind of stepping stones to make major discoveries. The problem by itself perhaps may be unimportant, but you are led to make fundamental discoveries like these beautiful objects, structures of these rings, and so on and so forth. So another important thing that Dedekind proved is the analog of unique factorization of natural numbers. He showed that every ideal in this ring can be factored as a product of prime ideals uniquely. So O sub k, he showed further that every ideal, every non-zero ideal of O sub k can be written as a product of prime ideals uniquely. This is the analog of the unique factorization theorem for natural numbers. Okay, so you can factor all the ideals uniquely, and inspired by the Riemann zeta function, he it turns he tried to define a zeta function. So here's how it goes. It turns out that this particular ring has the property that for every ideal A of the ring, the index of the ideal is finite. turns out it's finite. Index is finite. Every non-zero ideal, sorry. For every non-zero ideal, it's finite. And therefore, we can define, he defined norm, he defines the norm of an ideal to be this index. Okay? The norm of this ideal is the index. And he shows that the norm is a multiplicative function on ideals. That is, norm of A times B is equal to norm A times norm B. Therefore, it's a multiplicative function. Therefore, he defines the Dedekind zeta function. Well, he didn't call it the Dedekind zeta. We do now. Call it the zeta function of the number field. One over the norm A to the power S, where I'm running over all the integral ideals which are not zero. And because every ideal can be factored as a product of prime ideals uniquely, just like in the Riemann zeta function case, I can write it as an infinite product over and he managed to show that this thing converges for real part S bigger than 1. It's not difficult to show. And he asked the obvious question, just like the prime number theorem is about counting the number of primes up to x. He wanted to know how many prime ideals are there whose norm is less than x. So the analog of the prime number theorem he was making a guess. Let pi sub k of x be the number of prime ideals if you want to be a number theorist, you should learn how to make German calligraphic symbols, okay? Very important. It's a German P. Okay. To practice your calligraphy. Anyway, so you want to count the number of prime ideals whose norm is less than x. And I believe he was guessing this. Is this true? Okay. Now, it should not come as a surprise, especially because I've been dancing around this particular statement and not erasing it. This statement is the same as this, turns out. It's completely equivalent, just like in the case of that toy example, x squared plus 1 I gave you, all of a sudden leading to counting primes congruent to 1 mod 4. In fact, if the answer to this is this, the answer to this is also x over log x. It's completely equivalent. You would never guess it. So this is the beauty of number theory. This is why I do number theory. It's so fascinating that, firstly it's like, these sirens, in Greek mythology, these sirens, they attract these sailors or so, with their singing, right? These elementary problems kind of seduce you into paying attention and trying to study them. and then you're hooked, right? So it's something like that. But it's better than that. Usually those sailors got killed. We don't get killed. Okay. People who do number theory are rewarded. So there are rewards. So maybe that's a bad example. Maybe it's more like Krishna and his flute is a better example. Okay, so that's the problem. Now, how would you connect these two to the this question? Well, it has to do with, again, Dedekind's fundamental researches. So, so here I have told you that O sub k is a ring, and given a prime p, we may consider the ideal generated by p. The principal ideal in that ring, we consider the ideal generated by p. Okay. Now that's a perfectly good ideal. Dedekind's theorem tells me every ideal can be factored as a product of prime ideals uniquely. So these PIs are prime ideals. Distinct prime ideals, right? We have this unique factorization of ideals in this ring. And the question is, abstract theory is fine and dandy, but how do I get my hands on those ideals? How do you give me those ideals? Okay. So Dedekind came up with a recipe. So my first step is to show you that these two are equivalent. I just told you that, but didn't show it to you, okay? I have to show it to you. Now I have to do it through this theorem. So Dedekind's recipe is the following. So now every number field by the theorem of the primitive element can be written as Q of theta for some theta, right? So the theorem of the primitive element tells you that Q is some Q of theta, where theta is some algebraic number, and minimal polynomial, algebraic integer actually, minimal polynomial, let's say, is f of x with integer coefficients. So suppose I can now tell you my field looks like Q of theta, where theta is a root of some irreducible polynomial f of x. The minimal polynomials are irreducible, of course, you know that, right? So f of x is irreducible, you have that. Then here's how Dedekind gives you a recipe for finding those prime ideals p. So he says, take your polynomial f of x, now that you have it in your hand, and factor it mod p. That is, over the polynomial ring fp of x. You can, fp is a field, fp of x is a polynomial ring over a field. It's a Euclidean domain, therefore you can factor it as a product of prime irreducible polynomials. So factor it. I deliberately use the same symbols. Okay, so factor it as a product of irreducible polynomials. Then, having done so, look at the ideal P sub I generated by the number P and this polynomial Fi of theta. This is an ideal. This is an ideal sitting inside O sub k. Then Dedekind's recipe is, apart from finitely many primes P, so there's some finitely many primes P which you just have to throw out from the discussion. Having done so, then the ideal generated by POK is precisely P1 to the E1 P sub R to the E sub R. So in other words, if I throw away these, special primes, these primes are called primes that might divide the discriminant, which we'll not talk about, okay? If we throw those finitely many primes away, there's a kind of a one-to-one correspondence between the factorization of f of x mod p and the factorization of the ideal generated by p in that field. That's an amazing theorem. Very impressive, very, very impressive theorem. So that, who would have guessed it? Factoring a polynomial mod p is really factoring ideals in some number field like this. So now you can see immediately what it means for us to be able to solve the congruence mod p. Oh, there's one more point that I should tell you. I should tell you that the norm of the ideal pi is p to the degree of fi. I mean, this functoriality is so neat. The norm of these prime ideals is p to the power degree of fi. So to say that f of x is 0 mod p means that, to say that it has a solution, means that when I factor it, there's a linear factor here. That means there's a polynomial fi of degree 1, which means that there's a pi in here whose norm is p. And every time there's a polynomial, every time there's a prime ideal of norm p, there was a root there. So the number of roots here is equal to the number of prime ideals in the field whose norm is p. Very interesting. Therefore, it is not going to be a surprise now to see that this counting thing is really counting the prime ideals whose actually norm is p. Remember, prime ideals whose norm is p squared and higher contribute less to the sum. So those, we don't need to worry about those, okay? So I think from this, understanding this theorem allows you to establish an equivalence between this and this. They're completely equivalent in this sense, as terms of asymptotics. Everybody happy with this? Okay. So now we have a Tiberian machine which tells us how do you go about getting these asymptotic formulas. In other words, this is nothing but the so-called prime ideal theorem. So it's not a prime number theorem, it's the prime ideal theorem. That is, how many prime ideals are there whose norm is less than x? That's what's called the prime ideal theorem in number theory. So how do you count that? Well, I have this factorization. We need an analytic continuation greater than or equal to 1. Except for a simple pole okay, so this, now that you understand it, so this was a thesis problem for Heinrich Weber, who was Dedekind's student. He solved it. What he did was he actually counted the number of integral ideals up to x. So Weber counted the number of ideals with norm less than or equal to x. It turns out to be a lattice point counting problem. Not trivial, but once you formulate it as a lattice point. He counted that. He ended up by showing that this was equal to some residue of the some number, rho sub k, which I will not go into, plus O of x to the 1 minus 1 over the degree. D is the degree of the field. Now you guys all know about partial summation. So if I know the number of ideals of OK up to norm less than x, here, what is this? I can rewrite this as summation an over n to the s. After all, this is just an ordinary Dirichlet series, although it was constructed rather exotically. It's really a Dirichlet series again. A sub n over n to the s. What is A sub n? A sub n is the number of ideals whose norm is n. So summation n less than x is exactly this. Once you have this, you can use your partial summation lemma to show that the Dedekind zeta function has an analytic continuation up to real part s bigger than 1 minus 1 over d with a simple pole at s equals 1 and residue equal to rho sub k. Okay? So at least you now get the Dedekind zeta function analytically continued to the region at least real part s bigger than or equal to 1. Now the question is, before you apply the Tiberian theorem, you remember you have to have, what do we want to apply the Tiberian theorem to? Well, we want to apply it to zeta k prime over zeta k of s, right? Zeta k of s over zeta k of s is equal to, when you look at it, the usual logarithmic derivative, you'll have an analog of the von Mangold function, right? The von Mangold function is going to be equal to log of norm p if A is a power of a prime ideal and 0 otherwise. Usual extension of the von Mangold function, okay? Having done so, oops, there's a minus sign here. Having done so, what we really want is we want to calculate that. The Tiberian theorem tells you that if you have this Dirichlet series, it has analytic continuation to real part s bigger than or equal to 1. Well, we have it now. We continued zeta k of s up to 1 minus 1 over d. And therefore, this has a nice meromorphic continuation in that region. The only problem is this silly thing can be 0 again on the line 1. So we need to know zeta k of s is not 0 for real part s equal to 1. But the proof that that doesn't vanish, you know, is the same as the proof that we gave for the Riemann zeta function case. Because, remember, we exploited the Euler product. Everything is, all the coefficients are non-negative. Therefore, the proof goes through mutatis mutandis, whatever that means. Okay? Mutatis mutandis is Latin to say that without any change. Sounds good, so I used it. Anyway, so this proof of the fact that this doesn't vanish is the same as before. simple pole at s equals 1. Therefore, this is asymptotic to x by the Tiberian theorem. And therefore, you can do your partial summation business and get this. And then you've solved the problem of counting solutions of a polynomial congruence mod p using the theory of the Dedekind zeta function. There is, as far as I know, there is no other way that you can do this.